morning. I am Reggie, Associate Professor, Department of ECE. Today we are going to see about Unit 3, the network layer. How the network layer and how the protocols can be used. After completion of this topic, students will understand what are the constraint node and what are the important components of IP version. Constraint node. In IoT system, different classes of device coexist depend upon the function of the network. Think architecture may or may not offer similar characteristics compared to generic PC or server in an IT environment. Another limit is that this network protocol stack on an IoT node may be required to communicate through a unreliable path. The power consumption requirement on battery powered node impact communication interval. To help extend battery life, one should enable low power mode instead of that what is always on. Another option is always off, which means communication are enabled only when it is needed to send data. While it has been largely demonstrated that production IP stack perform well in constrained node, IoT constrained node can be classified as devices that are very constrained in resources, may communicate infrequently to transmit a few bytes, and may not limited security and management capability. This drives that need for an IP adaptation model where node communicate through gateway proxies. Device with enough power and capacity to implement a stripped down IP stack or non-IT. In this case, you can implement either a optimized IP stack and directly communicate with application server, or go for an IP or non-IP stack and communicate it through gateway and proxies. Devices that are similar to generic PC in terms of computing and power resources but having constrained network capacity such as bandwidth. These nodes usually implemented a full IP stack, but network design and application behavior must cope with bandwidth constraint. In the early years of network bandwidth capacity were restrained due to technical limitation. Connection often dependent on low speed modem for transferring data. However, these low speed connection demonstrated that IP could run over low bandwidth network. With a constrained network, in addition to limited bandwidth, it is not unusual for a packet delivery ratio to oscillate between low and high percentage. Large bursts of unpredictable error and even loss of connectivity at time may occur. This behavior may be observed on both wireless and narrowband power line communication, where packet delivery variation may fluctuate greatly through the course of the day. IP version. Over a 20 plus years, IETF has been working on transitioning the network from IP version to IP version 6. The main reversing force that a lack of address in space IP4 as internet has grown. IPv6 have a larger range of address that should not be exhausted for seen feature. Today, both version of IP over the internet, but more traffic in IPv4 application protocol. IoT device implementing Ethernet or Wi-Fi interface communicate the IP4 and IP6 by the application protocol may dictate the choice of IP version. For example, SCADA protocols such as DNP3i3, Modbus, and IEC are standard specified IP4. So there is no production implementation by vendor of the protocol. For IoT devices with application protocol defined by IETF such as HTTP, CAAQ, MEAQ and XMP, and both IP versions are supported. The selection of IP version is dependent upon this implementation. Cellular provider and technology. IoT devices with cellular modem are dependent on the generation of cellular technology as the data service offered by the provider. Serial communication. Many GLNC devices in certain devices such as manufacturing utilities communication through serial data is transferred using proprietary or standard based protocols such as DNP3, Modbus, IEC 60870. In past, communicating the serial data over a sort of distance should be handled over analog communication modem. IPv6 adaptation layer for some physical and data link layer for recently standard IoT protocol support IPv6, while the most common physical and data link layer stimulate the adoption layer for both version. Newer technologies such as IEEE 802.1.4, IEEE 109.2 and GU have IP3 adoption. This is reinforced by IETF routing protocol for LAN, which is IPv6. IoT protocol stack with LAN. Consider the model of 6 LOP WAN working group published RFC. but RFC 49 is a functional because it defines frame header for the capabilities of header compression. You can see how the structure it will be. Header compression will be there, fragmentation and mesh addressing. These header must be stacked in adaptation of letter to keep the concept separate while enforcing a structured method of expressing the quality. Header compression. IPv6 header compression was defined initially by RFC 4944 and subsequently adopted by RFC 6282. This capacity shrink the size of IPv6 and user datagram protocol. 8-byte header slow down to 6-byte combined in some case. Fragmentation. The maximum transmitting unit for IPs must be at least 1280 byte. The term MTU defines the size of largest protocol that can be passed. For IEEE 802.5, 176 bytes of MTU. This was the problem for IPv6. The larger MTU is carried inside 802 15.4 frame into a smaller one. Mesh addressing. The purpose of mesh addressing function is to forward packet over multiple hop. These fields are defined by the header, hop limit, source address and destination address. Analogous to IPv6 hop limit, the hop limit for mesh addressing also put upper limit on how many times the frag may be forwarded. Each hop decrements this value by 1, it is forwarded. Once the value of it is 0, is dropped and no longer. So assessment question, the maximum transmitting byte for IP must be 1280. The purpose of this mesh addressing function is to forward packet over the multiple hop. The power consumption require battery pod impact on a communication interval. Thank you.